Our final speaker tonight, a name that rolls much easier off my tongue, Cameron Cooke. He's a computer vision technology specialist at Airbus, responsible for the Airbus Group's digital transformation office. Cameron's passionate about applying technology to transform the way Airbus designs and builds aircrafts. Based in Toulouse, he works with a multinational team of computer vision experts to develop solutions to optimize Airbus's operations in 6 countries across 3 continents. Previously a lead engineer at Qantas, where he applied AI to a diverse range of projects, including modeling aircraft performance, satellite connectivity, financial hedging, and network optimization. He also holds a number of patents and a degree in electrical engineering from the University of New South Wales. Speaking today on The Sky is Not the Limit, Artificial Intelligence at Airbus. Please welcome Cameron Cooke.
How do we switch the display time? Hi, thanks again for the introduction. So I'm really excited to be here today to talk about artificial intelligence, and in particular computer vision, and how we're applying it at Airbus. Now, I'm going to start off by telling you a story. Are we on? That sounds a little bit better. Okay, so I'm going to start off by telling you a story, and this story is about how we're applying artificial intelligence at Airbus. Now, to tell this story, we need to set the context. And this is the context. It's a big number, it's 48 billion euros. Fun fact, that's twice the revenue of the government of Romania on an annual... I'm not sure what that says about the efficiency of tax collection in Romania, but that's that statistic, and that's true. 48 billion euros a year is the revenue Airbus commercial aircraft generates. So basically, Airbus commercial aircraft is in the business of building aircraft. We build, I think this year will be about 800 aircraft. And basically, these aircraft range from the A320 up to the A380, which, it's 400 million euro aircraft. It's got 4 million parts, 400 kilometers of wiring. It's the most complex moving object ever built by mankind. So when we talk about this is the context which I'm setting. This is the scale at which Airbus operates and the value that can be generated by this organisation. This is just Airbus Commercial. We've also got Defence and Space. So Defence and Space build aircraft like strategic airlifters. Space builds rockets for going to space. And there's also helicopters who, I think they do helicopters. This is the next number in the context, 7,471. 7,471 is the number of aircraft we have today on our order book. So basically, our order book is commitments airlines have made to us to buy aircraft from us. Now, this is a fantastic opportunity. Just our A320, which is our most popular aircraft, we have 500 billion euros worth of orders, but it's also a challenge. Customers want our aircraft now. Customers love Airbus aircraft. They sell like hotcakes, but it's a challenge. As I think I mentioned before, we make about 700 to 800 aircraft a year, and we've got to make 7,000 aircraft. So it's going to take us about 10 years to burn down this backlog of aircraft. So potentially you have to wait longer to get an A380 than a Dacia back in the day, but it's a real problem for us because we lose orders from airlines who want aircraft now, and we can't supply them with these aircraft. So the real challenge is how can we make aircraft faster? Now, many organisations talk about scaling as a problem, but we have scaling on a unique level. We have operations all across Europe, and again, this is just for Airbus commercial aircraft in Europe. Across Airbus, we have something like 50 different plants. Now, it's important to provide the scale of these different plants. Just in Toulouse, which is where I'm from in France, basically we do aircraft development, and we've got a number of final assembly plants. So in Toulouse, we do final assembly for the A380, for the A350, for the A330. So there's four production lines in Toulouse, there's 4 more in Hamburg, and 1 each, which you can't see on the map, in China and the US. And this is just for commercial aircraft. Now, just to provide an idea of scale, we're talking about buildings. Here you can see the production line for the A350. And from memory, that produces 12 aircraft a month. In the back, you can see the production lines for the A320. We're talking about buildings that are like hundreds of meters in scale. That's the A330, and that's the A380. Now, this is all backed by an industrial production system of unparalleled complexity. When we look at, say, the A320, for example, the wings are made in the UK, the back part's made in Germany, the front part's made in France, part of the tail is made in Spain. All of these parts need to be shipped across Europe to our different production lines in both Toulouse and Hamburg. So you can start to imagine the complexity of these operations between 50 different factories where all of these parts are made. How do we get stuff around? Well, I'm glad you asked, because we've got these things called belugas. Currently we've got 5 of them. Actually, no, sorry, 7. We've got 5 mini belugas, and we've got 2 big belugas, which fly, basically they fly around 11 different destinations in Europe. So basically this is how planes are born. That's literally what will happen is we'll load the front part of the aircraft into the beluga and then fly it around France to do all these deliveries. Now, here's where the presentation is going to go horribly wrong, or maybe it won't, because I couldn't put this in the pack. So this will help provide more of the context around what happens on our final assembly lines. And this is the A330 final assembly line in Toulouse. So basically what you can see here is the center portion of the aircraft, and what's happening is we're putting the wings onto the aircraft. The wingspan of this particular aircraft is 65 meters to provide a context of scale, and literally you can see them joining everything on. Now they're going to lift the whole section, and basically it's kind of like IKEA on a massive scale where you have to join all the bits together, and I hope these guys follow, I hope everyone's following all the instructions here. So these are all these different parts, they're coming from all these different factories, and one thing I want to emphasize is that even though Airbus is probably like one of the most technologically sophisticated organizations on Earth, we actually have very little visibility to this production process in real time. You probably have more visibility on an iPhone update than we do on like the progress of building a 300 million euro aircraft. So they're putting the engine pylons on. They're putting the second one on. I was worried there for a second. And voila, here you go. So this whole process, I think, the whole process for an A330 takes a couple of days. In the case of A320, which are smaller, I think it takes about 2 or 3 days for the production from all the parts going to the factory to the aircraft rolling off the end of the production line. And now, this is where it has gone horribly wrong. Oh, no, it hasn't. Perfect. So now I actually want to get, that's the context. Now I actually want to get to the meat, the reason why you're all here. Hopefully none of you came here just to hear a presentation about planes, which I could do this for hours. But with unbridled enthusiasm, but I'm actually here to talk about how we apply artificial intelligence. Now the team I work with is called the Analytics Accelerator. Providing the context that we're operating with billions of dollars, the Analytics Accelerator has the mission of accelerating the digitization of Airbus. So basically this means driving artificial intelligence into the business so we can deliver benefits. And like I said, you can imagine 1% on 48 billion euros is a heck of a lot of money. It's a heck of a lot of benefits. So maybe these are some of the different areas where we apply artificial intelligence. We've got about a team of, I think, about 40 people at the moment. We're growing to 100. And so far we've done, as of yesterday, we've done 49 different initiatives. So when we talk about the design of the aircraft, obviously we're in the business of designing new aircraft, and there's many different ways we apply artificial intelligence. Probably, I think, for me, what's the most fascinating way is when we design an aircraft, probably the most critical part of the aircraft is the aircraft wings. The wings need to be very, very strong. They also need to be very light. We also need to be able to manufacture them. They are also fuel tanks, so they carry all the fuel as well. And part of the testing we need to do is we need to understand how the aircraft wings will behave structurally when they fly through a gust. Now, the traditional method we've used is we use computational fluid dynamics to run a simulation to understand how the wings will react as the aircraft will fly through a gust. This is very computationally expensive. This is like, you can imagine just how long these simulations take, how much computational power is required to do them. However, we realized what we can actually do is we can train an AI model to predict what the outcome of a simulation will be. So this is a surrogate model. And basically what we can do is we can use this because we can predict what the outcome of a simulation will be in 100th of the time it takes to run the simulation, we can now test 100 times more wings. And then basically, once we find the wings that work really, really well, according to our AI model, what we can then do is we can go and run those wings through the simulation to validate the performance of the model. But we see a difference of about 1% between reality and simulation. But we can run basically we can model 100 times faster, so that's really exciting. There's another area which is supply. Another example of the scale of Airbus is Airbus buys 4 billion euros worth of aluminium a year, 2 billion euros a year worth of titanium. Yes, it's crazy, a heck of a lot of tin cans. But the thing that's really exciting is that there's these really small areas where if you can get a 1% improvement in the way we purchase aluminium, that's obviously a huge benefit. There's other areas, like when we're making aircraft, you've got this, what's called a buy-to-build ratio. Buy-to-build is the ratio of the amount of raw material that you need to their end result. So in the case of some components of the aircraft, the buy-to-build ratio is 10%. So if you've got a part that weighs a ton, we need 10 tons worth of raw material to produce that. Obviously, in the case of aluminium or titanium, this is very, very expensive, but also there's environmental impacts because aluminium's basically solid electricity because it requires so much electricity in order to refine the bauxite to make it. There's other stuff like we're doing robot optimization. We're doing a lot of modeling for airlines where we're trying to understand how airlines can operate their aircraft better so that airlines can reduce their fuel. So you've got stuff like trying to understand, could airlines operate aircraft more efficiently? Could there be better flight paths? So there's lots and lots of really interesting stuff. And obviously you can appreciate there's what I really want to talk about and there's what I was allowed to talk about at the conference. That's always the problem. That's always the problem. Yeah. All your questions will be answered. Okay, so moving on, basically this gives you an idea where what we've tried to do is we've been trying to embed specialists in our manufacturing facilities, and we're also trying to train up people on the shop floor. We've got a program where we're training people at Airbus who are interested in artificial intelligence, about artificial intelligence. And we've actually had 700 people go through the program and be qualified as data scientists. There's a point in time where the CEO of Airbus realized, he saw the potential for artificial intelligence, and he's like, great, to do this fully, let's just get some data scientists. Let's go and hire, 700 of them. And we had to explain, basically my manager had to explain to him, you can't hire 700 data scientists of it's like what you want. It's like, that's the reality of the situation. So what we've gone and trained people up who already work in the business, who are already invested, and know these they understand the processes back to front. Now to talk about something I'm really, really passionate about, and this is computer vision. This is my area of specialty and expertise. So the question that's all going through your head, why do we have this picture? This picture is about the Cambrian explosion, which happened 541 million years ago. Now you're also thinking, why is he taking a sudden turn into natural history? Well, the Cambrian explosion was a point in evolutionary history that lasted about 10 million years where life dramatically changed. And one of the dramatic changes that occurred was animals evolved eyes. And this is important. Vision is important. Think about the predator-prey dynamic. Before vision, basically predators would have to go around, they'd use their whiskers to go and find stuff to eat. Now they can see stuff. Now prey can see the world around them. This is you've got to understand how critically important this is. In the case of the human brain, 20% of the brain is purely devoted to vision. There's another 40% that's also used for vision to do visual reasoning and help us understand the world around us. So I think this really emphasizes how important vision is to sense, which is why it's so exciting, computer vision as a technology in terms of enabling computers to see and understand the world. There's also been a Cambrian explosion technology which has been driven by data and also compute. In the case of data sets, you've got data sets like ImageNet. We ImageNet 14 million images. It's absolutely unbelievable. It's really hard to comprehend how many images that is. And then you've got compute like the V100 from NVIDIA. I think it's 10,000 euros, 105 teraflops. And I think probably the most interesting statistic was as recently as 2007, this would have been the second most powerful computer in the world, and you can now get for 10,000 euros. So we got 18. But another fact, the amount of computational power used for deep learning and training models has increased 300,000% over the past decade. So let's go into more detail about computer vision. In the case of computer vision, you've got this collection aspect. So when we talk about collection, this is acquiring the raw data, because ultimately computer vision is a form of dimensionality reduction, where what we're trying to do is we've got very high dimensional raw data, and we're trying to transform that into high-value features we really care about. So this could be, say, classical, so just like a classical vision system in the case of a camera. But we're also using things like you've got LiDAR, you've got ultrasound, you've got radar, and in the case of Airbus, like we're doing a big project where we're using volumetric data from an ultrasound to do quality assessment for composite parts. So basically the wings on the A350, which is one of the aircraft we make, trying to detect flaws which are the size of a pinhead in something that's the size, like it's a volumetric thing, but it's got the same surface area as a tennis court, so it's a very, very challenging area. Then you've got your pipeline. So pipeline is basically the compute. This is your GPU. This is the processor where your algorithms are running. In our case, we're trying to do a lot of stuff at the edge because we've got to deploy solutions into industrial environments where it's very hard for us to run. It's very hard for us to run the cabling that's required because when these plants were designed, no one really envisaged that people are going to start trying to install cameras everywhere. So we don't have the network bandwidth, and we need to do the processing at the edge so that we're only sending these high-value features over the network. You've then got an analytics layer. So basically, the analytics layer is where you're getting these high-value features and you're doing analysis on that. And finally, you've got your application, which is a dashboard, perhaps we're showing to users. So this also tries to set the context. This is actually a plant where we're doing a project for one of the things we're trying to do, which is shop floor computer vision, which is looking down onto the shop floor and trying to understand where different objects are and what's going on. In this scene, you can see there's a number of people. Well, the people are inside the green boxes, but we've also got different objects. Is that falling off? That's good. I don't know. Is that better? Okay. Okay. Yeah, so we've got all these different objects, and on the shop floor, when we're building an aircraft, all these things are critical. Like, everything has a place. So around the aircraft, you can see like the different tooling, and there's a lot of safety issues if stuff's not in the right place. I now want to talk a little bit about the platform which we're building for computer vision. And here's a fantastic graphic which I've stolen from NVIDIA. Well, it's great. It explains everything I want to explain, which is, and it mirrors what I showed you before, where basically you've got this collection phase, you've got this track and inference phase, where tracking and inference is something, basically you've got inference, which is your deep learning, which is where you're doing object detection, for example. And even here, people think that deep learning is very complex. In reality, even using fairly simple algorithms or algorithms that have been developed in the past couple of years, which are getting fantastic results, even when we're not using the latest and greatest. So basically, you're doing detection to extract different objects, and then you're doing tracking because you want to understand how these objects are moving over time, and we also want permanence. So there's a big difference between having, actually, maybe an analogy, okay. So let's say we had a system that was imaging me on the stage. As I move around the stage, there's a big difference between doing inference on a frame-by-frame basis and getting all these, say, detections of a person where you don't understand, okay, on this frame there's a person, this frame there's a person, this frame there's a person, and tracking. Tracking tells you, okay, there was a person, but it's also the same person that whole time, which is really important. I also want to talk about the hardware we're experimenting with. So this is called the Boulder AI DNN cam. So basically what it does is it's a 12 megapixel camera, 4K. It's got an onboard NVIDIA TX2 because I know everyone loves hardware. They love the juicy details. But this is off the shelf, and I think it costs about €2,500. Interesting context, installing a camera in a factory often costs more than €2,500 per camera. So the camera itself isn't the camera and the hardware isn't the thing that's actually expensive, it's the installation. So basically, the great thing about this, as I mentioned before, is we can do the inference onboard the camera so that we don't need to send data off the camera. This is important both from a network perspective, where we're not congesting the industrial network with huge volumes of data, but also from a privacy perspective. The reason this is critical is that if you're only sending inferences off the camera, that's the metadata about the imagery. We could have a system in this room. The system might say, okay, we've got 97 people in the audience at these places, but we don't know who anyone is. And that's what's critical. Well, in terms of building a platform, what we're doing is we're trying to build a product where we can go to a factory and basically they can say, great, we love computer vision, and they have an industrial product which they can then take and install in the plant. And basically, by having this platform, you've got this low-level processing that's done on the camera. And then what happens is that you've got all these high-level features, and we can start to build these products on top of this platform. So let's say that someone comes to us and they're like, okay, I really want to know in this, like there might be an example, say, for fire exits, where someone might say, okay, we've got all these fire exits, we've got the exclusion zones. It's critically important that no one parks any objects in this exclusion zone, and we can say, great, we've got this object detection and tracking layer, and we can then just build this product which will validate that all the fire exits are free. Then someone else might come and say, okay, I want to understand more about what's happening in this factory. I want to know what the production rate is. And one of the classical things we can do is when you've got an aircraft and the aircraft's being built, you've got all the parts are coming to the aircraft. There'll be like, say, a trolley which might have all the flight computers on it, which we can see and recognize. We can understand that when someone is going to that trolley to get a flight computer to put on the aircraft, and there might be, say, 5 flight computers they need to install, because we can understand that that person is going backwards and forwards, we can understand how far they are through the process of installing a flight computer. And you might have like 20 or 30 people all working around the aircraft, all doing these different tasks. And from that, we can get a real-time understanding of exactly how the production's going. Very, very quickly, in terms of our roadmap, we're still exploring with computer vision. We're still very early in the stage where, when I say we're exploring, we're learning as a company, because computer vision is a very powerful technology, but there needs to be a lot of education about what we're doing with it and how we're applying it, because I'm sure everyone can appreciate computer vision has been used in some contexts in ways that aren't great. So for us, when we've got people like unions and we've got workers on the shop floor who are ultimately going to be impacted by this technology in the sense that it's going to change the way they work, and we need to explain how the changes are going to be positive and how their privacy is going to be protected. So going into doing a quick deep dive into one of our projects, basically this is a factory in Toulouse. This is where they're making Airbus A320s. This factory makes 16 aircraft a month. Out of 60 we make globally, so it's about 27% of production. And basically aircraft, when aircraft are built, aircraft go through what are called stations. So all the aircraft parts come into the building and complete aircraft leave. For example, there might be one station where the front part and the back part of the aircraft are joined together. There might be another station where the wings are joined onto the aircraft, and there's another one where they put the tail on. And then throughout this whole process, all the different components are being installed into inside the aircraft. So it's just like Lego or Meccano or IKEA, where the final assembly line, or the FAL, is where all the parts come together. So every 20 hours, a siren sounds and aircraft move from one station to the next, and you can actually see that happening where an aircraft's being lifted up and then it's going to be carried forward through the factory to be parked somewhere else. So we've got this goal. We want to save, of that 20 hours, we want to save an hour of takt time. So basically, takt time is that 20 hours where the siren goes, the aircraft moves from one station to another. So what we're doing is we're installing a system into this factory where we're putting in 4 different cameras. To give you an idea of scale, the cameras are around, say, a 50-meter square looking down into the production line. And we're building a 65-class object detection and classification engine that's running on our platform. So from that, what we can do is we can detect and track all of the different objects around the aircraft. And here what you can see is that's, like I said before, that might be the bin that contains all the flight computers. That thing there might, say, have stuff, I don't know, the air conditioning. This one might have the overhead bins in it. So what we can do is we can understand from this what the production's like. There's also a number of other questions we want to answer. So, for example, we want to know when stuff arrives at the aircraft and when it's placed around the aircraft, because obviously with an aircraft, it's not really optional to kind of install some parts and kind of not install others. Everything has to be right. Like first time, it just has to be right. So we can understand where stuff's placed around the aircraft, because everything, like I said, everything has its place, and there can be safety issues if things are placed in the wrong location. We can also understand when people are going to these different parts bins and collecting all the parts. And we can also understand like the way all the different vehicles are traveling around the plant, because there's some places vehicles can travel and there's other places they can't. And it can be a safety issue, for example, if you're, say, pulling a trolley and that might hit someone or might hit something. So this is really, really important for safety. And finally, just to finish off talking about computer vision, probably the thing which I'm proudest about or most excited about is trying to apply computer vision in the shop floor. One of the things we're experimenting with is trying to do real-time redaction. And this is actually, technically, this is fairly simple. Basically, what you're doing is you're doing object detection and semantic segmentation, background extraction, all of these kinds of things coming together to try and detect people in an image and then redact them or remove them from the image in real time. This is really important because when we're building models, we need lots of training data. And the thing is, when we've got this training data, we want to be able to go to the workers on the shop floor and say, we've collected 200 hours of training data. There's no one in it. There's no people. It's really important to both, obviously, you've got GDPR, so you've got privacy issues, but even more fundamentally than that, I think people, there's obviously this right to privacy and this expectation of privacy. And the challenge is not technological, it's how we can deliver these solutions while meeting societal expectations. So it's a little bit hard to see there, but basically we've tried out different techniques, either just cropping people out, blurring them, and the most advanced one, which unfortunately is a bit hard to demo, which is where we just replace people with the background, so you can't see that someone was there in the first place. Which is pretty funny when they're pushing a trolley and the trolley's just sort of magically moving along. So now we'll go on to some questions, but just before we do, one of the things I find magical about working for Airbus is the advance in technology, where it's not just about artificial intelligence, it's about aviation. So in the same factory where we're doing this proof of concept, it was where we built the first commercially successful short-range aircraft, the Caravelle. It's where Airbus built its first really big hit, which was the A300M, which is the first commercially successful twin-engine long-range aircraft. But who cares about those ones? It's also where they built the Concorde. So questions? Okay. Okay. So I think the context behind security surveillance is that the security surveillance equipment has been installed and people understand why it's there. In the case of computer vision, it's really challenging. Like I said before, the challenge isn't technical because the challenge isn't technical. All this stuff can be done. What we're doing isn't, I'd say what we're doing is ambitious in terms of, I think we're very advanced putting this stuff into the shop floor, but the technology we're using, like for example, we're using yellow V2 as a detector. It's not something that's crazy complex or out there. No, sorry, yellow V3. But the challenge is what people will allow us to do, because obviously we've got workers and we've got unions, and obviously it's really important that we respect we respect all our stakeholders. We absolutely could probably go and stick stuff in, but I don't think that's not the right attitude to have when obviously you've got employees and they have to understand why the technology is there, and they have to feel safe and confident about the fact that their privacy is protected. And that's something that's really, really important in Europe. Obviously, there's lots of, and that's one reason why we're doing all this stuff in-house, is that we've got control over it and we can build a solution that meets our requirements. Absolutely. So this is the whole point, where computer vision by itself a computer vision platform doesn't deliver any value. The way it delivers value is giving us all of these high-level features that we can use to optimize our high-level, do all these process optimizations. And this is data we've never had before. That was probably the key thing which I didn't emphasize enough, is that there's so much data we can now collect we've never had before in 50 years of building aircraft. So that's why it's so exciting. Sure. So, yeah, an example. So basically, we're doing a trial in a plant where they make the engine pylons. It's the bit that bolts the engine onto the wing, pretty important. And I was going to say, I'm not an aerospace engineer. I understand the engine's meant to stay attached to the wing. That's generally that's a hard constraint, as they'd call it. In software, that would be a hard constraint. So in this plant, there was a very sophisticated model about there's a very sophisticated simulation of the plant, a digital twin, which said, okay, based on the production schedule, this is exactly how many times a vehicle should be going through this intersection. There was a schedule which would say, okay, at 17 minutes and 30 seconds or 9:37 in the morning, a forklift will go this way. Then there will be a truck going this way, then this, then this, and this. And according to the simulation, there should never be any traffic jams. Guess what? There's always traffic jams, and no one can work out why. So we put computer vision in, digitized what was happening over 200 hours worth of data. Turns out that people love driving golf carts around. That's the thing, it's like this was something that wasn't never modeled, and this was something that was never accounted for and never modeled. But that's the reality of the situation, was that people who we thought were walking were actually taking golf carts. So we saw 25% more movements, and guess what? You encourage people not to use golf carts, and the traffic jam goes away. In terms of, sorry? I wouldn't even say that. We're sorry. Do I need to stop now? Or? Okay, I'll just finish off really, really quickly. Thank you so much for your time. But yeah, we're not monitoring, we're not punishing people, but we want to understand at a high level and aggregate what's really happening, and that's something which we've never been able to do before. Well, thank you so much for your time. It's an absolute pleasure.